Hi everyone, this is Ramalinga Prasad Kuppa. Welcome to my channel, Pharma World. Today's topic is water content determination by Karl Fischer Titration method. Let us understand the basic principle. It is reaction between iodine and water in the presence of sulfur dioxide. The equation may look like this. Iodine reacts with water in the presence of sulfur dioxide to form sulfuric acid and hydrogen iodide. This is a simple reaction between iodine and water molecules in the presence of sulfur dioxide. The solvent in which the reaction takes place is generally methanol. But in certain cases where aldehydes or ketones are analyzed, special reagents like hydranol K may be used because aldehydes and ketones may react with methanol to form additional water. The reaction occurs quantitatively until all water is reacted. This reaction is quantitative and hence very specific for determination of water content. Since entire reaction is dependent on the amount of water present, it is most important to keep the entire Kf set dry, free from water or wetness. Since the reaction is very sensitive to water, it is necessary to make the Karl Fischer titration set totally dry and free from wetness from any external source. To achieve this, you can have a system. A system may be to protect the open ends of the Karl Fischer titrator with active self-indicating silica gel tubes. So the system is to protect the open ends of the titration system from ingress of moisture is fixing the active silica gel tubes. The open ends include the burette, the Karl Fischer reagent pumping system, vents, etc. Active silica gel means the self-indicating blue silica gel granules. It is called self-indicating because as the blue silica gel absorbs moisture, it turns pink. So it is necessary to make sure that the silica gel in the protective tubes is always blue in color. Used silica gel, which is pink in color, can be regenerated by drying at 120 degrees centigrade or 150 degrees centigrade overnight. Then it turns blue. Cool it in a desiccator to room temperature before refilling the protective tubes. You can use molecular sieves or alumina granules also for the purpose, but they are not self-indicating. Of course, they are expensive too. Let us see how it works. The Karl Fischer reagent could be prepared by using a combination of dry methanol, iodine, pyridine and sulfur dioxide. The Karl Fischer reagent can be prepared by mixing necessary quantities of methanol, pyridine and iodine and cool in an ice bath. Pass adequate amount of sulfur dioxide till a Kf reagent with a factor between 5 mg per ml and 6 mg per ml is obtained. Store the prepared reagent in a low actinic glass bottle, preferably in an amber colored bottle, and store in a dark and cool place. But for routine usage, handling of sulfur dioxide, pyridine is cumbersome and health hazard too. But you can try once or twice just for fun. Ready-made solutions are available as one component reagent or two component reagent. One component reagent or two component reagent are available in the market. the one component reagent can be used instantly, whereas the two components have to be mixed before use. There is a sequence to mix also. It is always solution A is mixed with the solution B and not vice versa. Hydronal is another one component reagent replacing the routine solvent pyridine. The hydronal composite is a good one component reagent that works for ketones and aldehydes also. It has also the additional advantage of replacing the health hazard material pyridine. All the reagents used for Karl Fischer titration should be stored away from light and potential water contamination. So it is very important that the reagent is protected well, always away from water and in a low actinic glass bottle. Let us try to understand what is a Karl Fischer reagent factor. This factor is used to declare the capacity of the Karl Fischer reagent. This is a measure of water equivalent for each ml of the reagent. Generally, it ranges between 5 to 6 milligrams of water per ml of Karl Fischer reagent. For example, if the Karl Fischer factor is 5.023, means each ml of Karl Fischer reagent will neutralize 5.023 milligrams of water. For example, if you take a sample and it consumes 1 ml of Karl Fischer to neutralize. That means the sample that was taken for determination of water has a water of 5.023 milligrams. Since the reagent is very sensitive in such a very low levels of water content, it is necessary to check every day for its factor because it is likely to change. Let us see how the standardization of Karl Fischer reagent is carried out. Either sodium tartrate dihydrate or purified water is used for standardization of KF reagent. Purified water is 100%. So there is no additional factor used in calculation of the KF factor. When sodium tartrate dihydrate is used, it has a constant water content of 15.66%. This is a constant amount present in sodium tartrate dihydrate. The calculation is as follows. See the molecular weight. It has 46 grams of sodium, 48 grams of carbon, 4 grams of hydrogen, 96 grams of oxygen plus 2 molecules of water with a weight of 36 grams. So the total would be 230. So the calculation is like this. So 36 grams of water present in 230 grams of the total molecular weight into 100 would give you approximately 15.6521% of water. This typical characteristic of sodium tartrate dihydrate makes it a standard to determine the factor of KF reagent. So sodium tartrate dihydrate has two water molecules firmly attached to the molecule. This specific characteristic is used for standardization of Karl Fischer reagent. Let us see more. When using sodium tartrate dihydrate, you have to take quantity between 20 mg and 125 mg for standardization of Karl Fischer reagent. So it is recommended to take 20 milligrams to 125 milligrams of sodium tartrate dihydrate for determination of Karl Fischer factor. If you use water, it should be between 2 mg and 250 mg. Fill the KF titration vessel with dry methanol so that the active part of the electrode dips well, approximately 30 to 40 ml will be sufficient. So here it is very important to see that the electrode dips in the solvent. If some other solvent is replaced for methanol, at least 20% of methanol also should be taken into the KF titration vessel. Diethylene glycol, monoethyl ether, or any other suitable alcohol is used, it is necessary to use about 20% of methanol with that solvent. 5 ml capacity burette is recommended for more accurate results. 5 ml capacity burette with a least count of 0.05 ml is recommended for accurate results. Sample quantity for water determination should have approximately 2.5 mg to 22.5 mg of water. This will be between 10% and 90% of the burette capacity of 5 ml. Sample quantity should be taken in such a way that it contains at least 2.5 milligrams of water or 22.5 milligrams of water on the maximum side. 2.5 milligrams will be equivalent to 0.5 ml for a factor of 5 mg per ml. So 0.5 ml will be 10% of the burette capacity of 5 ml. Let us see how it is calculated. For a Karl Fischer with a factor of 5 mg per ml, 1 ml will be equivalent to 5 mg. So 0.5 ml will be equivalent to 2.5 mg. 0.5 ml is 10% of the burette capacity. It's a simple calculation. Similarly, 22.5 mg will be equivalent to 4.5 ml, which is 90% of the burette capacity. So 22.5 mg will be equivalent to 4.5 ml. That is 4.5 ml into factor of 5, that will be 22.5 milligrams. And 4.5 ml will be 90% of the burette volume. Is that calculation simple? Is it clear? Let us see the calculation for standardization. If sodium tartrate dihydrate is used for standardization, calculate as follows. Weight of DST in grams, 15.66 divided by 100 into 1000 divided by the Karl Fischer volume consumed in ml. If DST is selected for standardization, there is a factor for water content. It will be 15.66 divided by 100. So this factor comes into picture. Factor 1000 is used for converting grams into milligrams. If purified water is used for standardization, calculate as follows. Weight of water in grams into 1000 divided by Karl Fischer volume consumed in ml. It is just like similar to the one calculation which is done in the above example. Entire calculations are based on milligrams per milliliter. So the factor after standardization would be mg per ml. Let us see how the water content calculation in a sample is done. Let us assume that the factor for Karl Fischer reagent is 5 mg of water per ml of the reagent, and the titer consumed for a sample of 1 gram is 5 ml. Let us see how easy to calculate the water content if you know the basic principle of calculation. So 5 ml is equivalent to 5 mg into 5 ml, that is 25 mg of water. This is present in 1 gram of sample. So 25 mg divided by 1000, which is 1 gram, is converted into milligrams. So 25 divided by 1000 into 100 will give you percentage, which is about 2.5%. Let us see a couple of examples. Let us suppose that for standardization of Karl Fischer, 12 mg of water is used and it consumed 2.3 ml of Karl Fischer reagent. So the calculation is very simple. The calculation would be 12 milligrams divided by 2.3 ml. That will be 5.217 mg of water per ml of Karl Fischer. This is called the factor for KF reagent. Now let us suppose another example where 1.256 grams of sample consumed a titer value of 4.2 ml with a factor of 5.217. So the calculation will be 4.2 into 5.217. That will be 21.9114 milligrams of water present in the sample of 1.256 grams, which is converted into 1256 milligrams. So the calculation would be 21.9114 into 100 divided by 1256. That will be 1.74%. There are several methods described in pharmacopoeia. Most of the time, the direct titration method as described in this video is used. You can read USP chapter 921 or PHEUR, that is EP 2.5.12 or Indian Pharmacopoeia IP 2.3.43 for more details. I hope that you understood the subject well and the intent of Karl Fischer titration methodology is understood well. Thanks for watching. For more videos, please do subscribe, like and share. Thank you.